Please, you can start.
Yeah, hello everyone. So today we are going to discuss advanced solidity. It is like the first lecture of advanced solidity in our course. There will be 3 lectures, and yeah, they're pretty hard to understand and like difficult to comprehend. So if you have any questions, please ask right away and I will answer them, because yeah, it will be like quite difficult. So today's topic is assembly and data allocations that I like already touched several lectures ago, but today we're going to discuss them like in more detail. So first of all, let's define what opcode is. The opcode are like EVM instructions that the smart contracts bytecode consists of. So basically opcodes are the tiny bits of bytecode or tiny instructions of bytecode, which together create the smart contract. So basically opcodes are tiny instructions that represent what function has to do and how it has to do. Opcodes can push or pop elements to or from the stack. They can access memory, they can access storage, they can read call data, and also they can manipulate return data. Opcodes are used to call and create other contracts as well as emit events. So basically, opcodes are like instructions to EVM, what to do and how to do. They can add 2 values, like taking them from the stack and pushing the result on top. They can call other contracts by taking the address of the contract to call and some payload, and etc. etc. Here is example of those opcodes. So there are a lot more, of course, but I have taken several for you to understand. For example, here is the opcode add. It adds 2 variables by taking them from the stack and pushing the sum of those variables to the stack. This is the hexadecimal representation of this opcode. So if you inspect the bytecode, like the raw bytecode of the smart contract, and see the value 0x01, probably it is the opcode add. The opcode caller, which is the message sender, the mload opcode that loads the chunk of memory and loads this chunk to stack. A store opcode that takes the value from stack from memory and writes this value to storage. Push 32, which pushes 32 bytes to stack. Delegate call opcode, which calls the smart contract with some delegate logic, and create 2 opcode that creates smart contracts depending on their bytecode and the address of the factory that deploys those contracts, which has like a deterministic deployment. Yep. So what is Yule? Yule is a like solidity assembly, or the programming. Actually, Yule is a programming language, a standalone programming language that can be used to write smart contracts on its own, and also like some part of this language is used by Solidity and can be accessed by like special syntaxes, which will be shown on the next slides. So Yule is directly translated to opcodes and has to be used with extreme caution, because high-level Solidity provides several checks, several like assertions that, for example, if you try to like add two variables, they will overflow, and the Solidity like explicitly checks that, and in case of overflow, reverse the transaction. But U is too low level, and it doesn't perform those checks. So it has to be used only in those cases where you're really confident that this is the way to use it, or like where you like understand that certain optimization is needed, and also can apply YUL for that matter. But never use YUL just for fun, like never. It is not safe at all. Also, with the introduction of new compilation process, which is called intermediate representation compilation, Solidity compiler now takes the Solidity code, first translates it to YUL, and then optimizes the YUL, which is more low level, and then translates already optimized YUL to the bytecode. Because of this intermediate representation, compiler is able to optimize like code more efficiently. So IR compilation is more efficient and should be used today. So let's take a look at simple smart contract that I have written in Solidity that will like expand and understand how EVM understands, interprets this contract, and at the end we'll get the same smart contract, like semantically same smart contract, but written in YUL programming language. So it is rather simple. We have a contract named example. It has a function sum, which accepts two arguments. Most of them are int256. It returns int256 as well. And what it does, it just basically adds those two variables and returns the summary. So let's complicate the contract a bit and introduce inline assembly how it is done in Solidity. Of course, it is a simplified version. I wanted to show how to write in assembly here, but of course I omitted really important checks. For example, the overflow check. So on the previous slide, Solidity starting from version 8 automatically adds the check that those two and that the summary doesn't overflow, but assembly doesn't do that. So the summary may overflow, which might bring errors and exploits. But yeah, it is the same function. I define the variable result, and then with a special syntaxes, assembly syntaxes, I add those two variables using the opcode add. So this is like a usage of an opcode add, which accepts two parameters, the first variable and the second variable, which have to be placed on stack. So it will pop those two elements from the stack and push the result onto the stack, which is done like here by assigning the result to result variable. And after that, I just return the variable from the function. So pretty simple right now. Then let's add more inline assembly, which is also a bit simplified, but still, what do we have here? The function signature is the same, but now I am defining the variable result inside the assembly block. So this is like pretty much the same as in the previous example, but the variable defined inside the block. But here, on the next two lines, I'm using two opcodes. The first one is mstore opcode, which accepts the memory location where to store the result, and 32 bytes of the variable that I want to store starting from this location. So basically, it writes our result into memory starting from a 0 pointer. So first 32 bytes of memory will be occupied by our addition result. And then I'm using the return opcode, which accepts the memory location where to take the value from, and the length of this memory chunk to read and to return from the function. So basically, this opcode terminates the execution and marks the execution as successful. You may also use the revert opcode, which basically does the same. It takes the starting memory location, the length, and places, reads this memory, places whatever is read into the return data, and reverse the transaction, so marking it unsuccessful. But here, yeah, everything's fine, so they're just returning the result. Pretty simple here, but let's go to a sort of extreme. This is the same smart contract that was originally in our part 1 example, but right now I have rewritten it into YUL completely. Let's quickly go through the code so you could understand what's going on here, but of course you have to understand that it is also a simplified version. I have omitted really important checks here, so that the code is more readable. Here I define the object example, which is the same as contract example. Then draw two chunks of code. The first one is the code chunk that is executed during the constructor phase. So this chunk of code is going to be executed when the smart contract is deployed and its constructor is called. Basically, what this code has to do is apply changes that you want to do in the constructor. For example, set the owner of the contract, apply some, I don't know, constants or immutables. I don't know, do whatever you want. But what it has to do, it has to return the code, like the runtime code. So here is the difference between the init code of the contract and the runtime code of the contract. So init code of the contract is basically the whole chunk of the contract that is output by the compiler, but the runtime code is the code that is returned by the constructor. So you will apply the changes here and return the runtime code in the constructor. So what those two lines do here is that data copy basically writes, so it reads the bytes of our runtime code and writes those bytes to memory starting from location 0. And after that, the return opcode reads those bytes starting from location 0 and returns to return data, so EVM could create this contract for you. After the contract is deployed, the object runtime will be available to call. And we also have the code section here. So what's happening here is that I define a switch statement, which goes through the selectors of the function. So you remember that in order to call a certain function, you have to set the selector of this function. So encode the selector of this function in the call data, and Solidity will like go through the functions one by one and define which one you're calling. So here I'm doing this manually. So I have calculated the selector of our example function, and the selector is this. And the function that I'm calling is right here. So I'm loading the data, our call data, because selector is like the first 4 bytes of our call data. So I'm loading it here. This opcode loads 32 bytes of call data. So I have to shift those 32 bytes to the right. So I get only 4 bytes in the end. So I'm shifting the 32 bytes by 224 bits and getting 4 bytes in the end, which is the selector I want. Then I compare the selector from the call data with the one hard-coded here. If they match, then I am calling the function sum. Also, I remember that uint256 variables are presented in the call data just as they are. So what I have to do is load the 32 bytes of call data starting from the first byte, which is right after the selector. And this will load my uint256 variable, because 256 bits is 32 bytes. Here I have loaded the variable A, and on the next line, I'm loading the variable B, which is placed right after variable A. So this is how ABI encoding works. Okay, I have obtained 2 variables, A and B, and then this is already familiar code to you from the previous example. I am using the add function or add opcode to add A and B together, and like receive a result. And I am also passing this result directly to mstore opcode, which will place the result in the memory starting from position 0. And after that, I'm reading the memory starting from position 0. I'm reading 32 bytes of it. 0x20 is hexadecimal. So in decimal is 32. So reading first 32 bytes, which is exactly our sum, and return opcode terminates the execution of the contract and places whatever it has read into return data, which can be read by, for example, front end. So this returns the sum. What I have also added into this code is the default statement of the switch operator, that if there are no selectors that there are, then we are just reversing and returning nothing. So this will just silently revert the transaction, and you'll never understand why. But yeah, it's just an example. So this code is legit. Yeah, so this is the yield example. It is pretty low level, and you have to, or you should use it only when you're confident what you're doing, and not just for fun, because yes, Solidity is like high-level language, and it its compiler understands what checks to add in order to be safe for you to use this language. Because in, for example, before Solidity 0.5, there was like a bug of Solidity compiler that users would use to, for example, trick certain functions to like think that they are providing more value than it should accept. So this bug was named shared address attack, and it actually drained a lot of money from exchanges due to simple limitation of Solidity compiler. And they have fixed it in 0.5 version. But if you are using Yule directly, you have to consider those like mistakes yourself. And there are a lot of mistakes to consider, so only write this low level code if you're confident. Okay, so let's just quickly go from like assembly to data allocations and quickly talk like in more detail which data allocations EVM uses and how it does it. So the first and the most important, actually, the stack data allocation and opcodes that are like bytecodes manipulate stack. So some opcodes pop elements from it, some opcodes push. And also there are opcodes for arithmetical operations, opcodes for calling smart contracts, opcodes for creating smart contracts. But all those opcodes some like interact with stack somehow. For example, calling a smart contract, the opcode accepts the address of the smart contract to call, from where in memory to read the like caller arguments data, the length of those arguments, and etc., etc. So those parameters to certain opcodes have to be placed onto the stack in certain order, so that opcode could take them, pop from stack, and do what it has to do. Also, Solidity compiler remembers where the values of local variables are and where they are stored on stack. So stack in EVM only holds like variables. It doesn't hold opcodes. Opcodes are stored in the bytecode, and opcodes only manipulate stack. So in some way, this like might be thought as sort of magic, yeah, that how does Solidity compiler remember all those local variables? How does it understand that like variable A is here and variable B is there, and that variable A is like on the top of the stack, and variable B is like right beneath the A in the stack. But this is what compiler does, and this is what compiler has to do so that the language is usable. And all of that is handled by the compiler. So it is like its job. Also, the important thing is that opcodes are laid in the reversible extentation, so in the postfix notation. And what I mean here is our human readable notation is A plus B. So I don't know, 3 plus 5. But for compiler, what will it do is it will place those variables in a way so that it will be readable as 3, 5 plus, because 3 and 5 will be placed in the stack, and plus is the operator that will be applied to the stack. And after that, the result of the addition will be also placed to the stack. So this notation is called postfix notation, You can read about it online. It is actually how calculators work, how they understand that multiplication has to be applied first before the addition. So this is also done by the compiler. And important limitation by the EVM is that stack size can't exceed 1024 elements. If it does, EVM reverses the transaction. What I mean by stack size is that, for example, you have a recursive function that calls itself. If it calls itself too many times, the stack will grow to more than 1024 elements, because stack has to keep all the arguments, all the return arguments, etc., etc. So I mean by calling not calling another construct, by just simply calling the function from the same construct. And in that way, you might exceed the stack and transaction will revert. Speaking of calling other contracts, there is a different limitation here, because like long ago, there was an EIP that introduced the limitation so that only 63 of 64 available guess is forward to the contract that is called, and 1/64 of the guess is reserved. And by doing so, the stack limit on those calls is only like reachable to 400 or 500 elements maximum. And let's just quickly go through how stack in our example, in our Solidity example works. So this is like quite hard to understand, but you can like watch this video after the lecture and just take a look at the example, take a look at this slide, and understand it for yourself. But I will talk about this as well. So number one, Solidity places the function selector on the stack via call data load. The opcode arguments also pushed and popped. So what I mean here is that the arguments that call data load opcode takes are first pushed to the stack. Then once call data load opcode executes, they are popped by it, and call data load loads the selector from call data and places this loaded selector onto the stack. Then Solidity pushes our selector from some function to stack and compares it with the one that it loaded on the previous step. Then, if the comparison is successful, the values of A and B variables are pushed to the stack via call data load as well, and also pointers to the call data from where to take those arguments are pushed as well. And once call data load opcode executes, it takes those pointers, pops them from the stack, and places the values that correspond to A and B in our call data. So A and B are now on the stack. When we are calling the add opcode, the A and B values get popped from the stack, and the sum gets pushed. For example, if variables A and B are used further like the function, then A and B will get pushed once again onto the stack. So at some point of time, we'll actually have two A's and two B's on stack, and after the add opcode, which consumes the first two stack elements, those duplication will not take place after the code execution. And number 5, the mstore opcode, the mstore opcode pointer gets pushed to the stack together with the value that this opcode accepts to place under this pointer. So those two variables are pushed on stack, but one of them is the result of our add opcode, so only the pointer gets pushed. And we have pointer and our summary result on the stack right now. After the mstore opcode execution, both pointer and sum gets popped. And finally, the return opcode arguments are pushed. These are also pointer and the length of the data to read. So when opcode executes, it pops both elements from the stack and writes to return data, which are then returned to the Kali of this contract. So let's then talk about memory. Stack, I hope, is clear, but yeah, what about memory? So first of all, memory is a mapping between pointers and slots. So in EVM, memory can be sorts of like a traditional memory in your operational system, but it is a bit different here. You can also allocate it and destroy it, but it is a bit different. First of all, the maximal value of a pointer is 2 to the power of 156 minus 1. This is a lot of memory to access, much more than in your operating system. But what does it mean? So yeah, this is a lot of memory to access, and of course, this much memory to allocate is too many resources, and you have to somehow limit the available memory in EVM. And actually, how EVM does it is that it keeps track of which memory pointer was used and keeps track of the maximal memory pointer. And if you are accessing the memory after this tracked maximal pointer, you will have to pay gas for that. And this is called memory expansion cost. And the actual cost is quadratic to the pointer that is used. So at some point of time, if you're using too much memory, you'll just run out of gas, and no Ethereum could pay for this execution. Memory is divided into 32-byte slots, or called slot values, whatever. And which is important, there is no element blocking. So what I mean here is that in storage, for example, you can have two variables, let's say of type uint 128. So together they consume 32 bytes, and they will be placed into one storage slot. Memory doesn't work this way. Every individual element will be placed into an individual slot, regardless of its dimensions. If it is Boolean, if it is uint A, if it is enum, that value will be placed in the separate slot. And memory is reset every time you subcontext is called. So when you're calling a contract, the memory is like freshly allocated. But what is more important is even though this memory is fresh, you just don't have to take for granted that there is no garbage in this freshly allocated memory. And what Solidity does, for example, if you're allocating an array, a memory array, first of all, Solidity clears this memory for you and then allocates the array. And if you're using assembly, this allocation has this memory cleanage has to be done manually, which you might just forget and receive bugs for that. So memory is a tiny, tricky structure in Solidity because it has pointers that do something like in Solidity. Memory is not even in Solidity. There are certain memory locations that stand for other memory locations. So here is the table of EVM pointers, it's memory. And in the first category, we have Solidity scratch space. Those are two memory pointers that start from 0 and end at 40. So two slots, two 32-byte slots. And they're used by Solidity to like do quick stuff. For example, the hashing results, the return data, if it is like less than 64 bytes long, may be placed here. And usually those two slots are dirty and they may be used like by Solidity at any point of time. Then there is one slot which is super important for Solidity. It starts at pointer 40 and ends at pointer 16. It is called free memory pointer, and it stores the pointer to the next location where the free memory is. So once again, at address 40, so 40 is the pointer to the slot number 3. Slot stores the pointer to the free location, to the free memory location. So on this example, the 80 stored here, which refers to that slot. And this means that starting from position 80, the memory is free and can be used. And let's say that a function foo, and you're allocating a memory array of 10 elements. So you remember that for each element, like 32 bytes of memory is used, like regardless of the type here. So this means that 10 elements of 32 bytes, and this is 220 bytes. And also with that, the length of the array is stored. So which translates to 340 bytes. And when you're allocating this memory, what Solidity does is that it reads the free memory pointer, understands that it points to location 80, and starting from location 80, it like reserves or allocates the memory. So it will allocate 11 slots here, and then override this free memory pointer to point to location 420. So 80 plus 214, and Solidity will update this memory pointer, point to a new location where it will use to allocate more arrays or whatever. So what is important is that this free memory pointer is never decreased. So it always increases and increases. There is no memory management in Solidity. There is only the increment of this free memory pointer, which is like used to allocate memory structures. What is important also is that sometimes Solidity may not increment this pointer and just allocate something in the free memory space and not update the pointer, like in order to optimize the gas usage. And because of that, you can be sure that the memory is clean. And for that matter, whenever the arrays are allocated, Solidity loops through every available. So Solidity loops through every slot that this array will use and explicitly clears those slots. So is not cheap in Solidity, and like is big O of n complex. Yeah, let me just quickly check the questions. Are fields of structs also stored in separate slots? Use their total size? Yes, if they are presented in memory, then they are not packed. Every element is stored separately. Oops. Yeah. Okay. Yes. Also, there is so-called zero slot, which is which is placed after the free memory pointer, and Solidity like never uses it, and it is pretty much always equals to 0. But I don't know actually, but maybe there are certain cases when Solidity writes to the slots, but yeah, usually it omits it. Okay, so let's move on then and talk about storage. Storage is another location where Solidity can store variables, and which is similar to memory. It is also a mapping between slot numbers and slot values. So those slot numbers are they are not usually like described as pointers. They are usually described as numbers, but you can think of them as pointers as well. And what is important, that those slot values are bound to a specific contract. I will explain a bit later what I mean here, but Solidity memory, rather EVM memory, is bound to a specific context, but slot values are bound to a specific contract, which is a bit different. The maximum slot number is 2 to the power of 256 minus 1, which is the same as memory. However, there are no allocation costs, or there are no storage expansion costs. There are just costs for reading the storage and writing the storage. Every storage slot holds 32-byte values, and elements might be tightly packed there. What I mean here is that in memory, for every element, there is a dedicated slot, but in storage, some of those values might be concatenated and stored in one slot, as one big value. This doesn't apply to bytes arrays and string arrays because they work a bit differently, and every element is already packed with different with other elements. So in memory they are also packed, but in storage they are packed as well. I am talking about separate elements, I don't know, two booleans, not an array of booleans, but actually other arrays are might be packed, but in memory they are not packed. Important, what is important about storage is that it is persistent and preserved between transactions. So if you have written something into the storage, then unless you clear the storage, this value would be preserved throughout the life of Ethereum. So if Ethereum dies or whatever happens to it, then of course you will lose the value. But if Ethereum works, then this value that you stored into the smart contract storage will be preserved for entirety. And depending on the current slot value, the value that you are writing right now, and the value before the transaction, the cost of storage is estimated. Actually, to understand how much gas you're going to pay, a lot of calculations have to happen, because it depends on the if the slot is a zero value or not, if it is the first time you're writing to the slot in the transaction or not. There are also warm and cold slots, so a lot of variables to consider. But yeah, what is important is there is no expansion. You only pay for what you do. And what I meant here, that the storage is bound to a specific contract. So in terms of a delegate call, which I will explain in the next lecture, the slot numbers and slot values are separated, which enables the proxy contracts to work and be used. So here is an example of the storage. Here we have a contract, a tiny contract on the left with the array defined in the storage space, with a function foo that just writes two elements to an array. Actually, probably I have missed the memory allocation here, but yeah, just imagine that this array is properly allocated and stored. Yeah, because I think that this code will revert, but yeah, I think you'll get an idea that I wanted to show here. The first idea is that there are certain rules in Solidity that are applied to certain elements to represent them in storage. And what happens to arrays is that the length of those arrays is stored directly in the slot this array occupies. So storage starts from slot 0 and goes like far beyond. Every construct has storage, and here, because the storage variable is the first one, it allocates the slot 0. And arrays store lengths in their allocated slot. The actual values of the array are stored starting from slot Keccak 256 of the array slot. So this will be some huge value, but what will happen here is, like, I am writing the value 1 to the 0th element of the array, and this value will get stored to the slot number Keccak 156 of 0. The value 2, which is the first element array, will be stored at Keccak 256 of 0 plus 1. And on the right is just the abstract picture of the storage, how storage like is represented. So here we have the key or slot number 0, which points to 0, and the value is here equals to 2, because the length of this array is 2. And so I have missed the line of code here. So 2 is here, and values of those elements are somewhere there. And yeah, these are the rules for arrays. There are rules for mappings. There are rules for like mappings of arrays and etc. etc. So they're applied recursively, but you will have to check the manual to like understand how each variable is presented in storage. For example, strings are presented a bit differently. Sometimes the length of the string and the values of the string may be packed together, sometimes not. So there are certain cases, and yeah, you'll have to check the manual for that. Speaking of cold data, which is another important location in Solidity, and cold data is used to call contracts or deploy contracts or call contracts within contracts. So how does it work? First of all, cold data is a sequential data location, which is very similar to memory. You can think of it as memory, basically, but yeah, it has certain like limitations. First of all, cold data is a read-only data location for smart contracts. So only low-level EVM, which is not accessible by smart contracts, not accessible by opcodes, can read values to cold data. Smart contracts may only read cold data, not write into cold data. For every 0 cold data byte, 4 gas is paid, and for every non-zero cold data byte, 16 gas is paid. Meaning that if you are calling a function and it accepts a lot of arguments, so there will be a lot of bytes in the cold data, you can count how many bytes out of this data are 0 and multiply them by 4. Then count how many bytes in this cold data are non-zero and multiply them by 16. Sum them up, and this will be the raw cost of this like data transmission. There are a lot of optimization tricks done here. For example, if you like follow the Solidity like news, you might remember that there was a tool called Vanity addresses that's used to like compute certain private keys for addresses that will have certain amounts of leading zeros in front. So this was all done so to, like, first of all, of course, having many zeros in the front is super cool. But second of all, having zeros in an address is less expensive to call. And many smart contracts use this trick to decrease the gas cost of their usage. And yeah, there are a lot of tricks for optimization, and this is like one of them. Then, when smart contracts are called, the new call data subcontext is allocated. So this is just the same way the memory works. So when you're calling a contract, the new call data context is allocated, and this smart contract can take whatever is in this call data is placed and use it. Usually, call data is ABI encoded, which is the standard for calling Solidity functions, which was developed for and by Solidity guys. So other smart contract languages might or might not use ABI encoding, but Solidity at least does it. And the call data field may be a smart contract init code in case of deployment transaction. So when you're deploying a contract, you're sending a transaction to a zero address and specifying the init code in the data field. Ethereum understands that you want to deploy a contract, so it deploys it, it takes the gas from you, and allocates the bytecode and the address for this smart contract. Yeah, just a quick example. Call data can be returned from the function, which is like a funny case in terms of Solidity language. And in that case, the call data will just be forwarded to the return data. So here is an example. To use the call data data field, you have to use the modifier call data instead of memory. And in that case, those bytes will be used directly from call data. And here I'm just returning these bytes, which is like kind of weird to see call data returned from the function, but it is valid Solidity, and it's just like a tiny optimization. But yeah, it's pretty much useless code. Return data, what is it? Return data is also a sequential data allocation, which is very similar to memory, very similar to call data, but like a tiny bit reversed semantically. Return data, contrary to call data, can be written by return and reverse opcodes. Return opcode terminates the execution and marks the execution as successful, and reverse opcode terminates the execution and marks the execution as failed. Return data always stores the value of the latest called smart contract. So for example, if you have a smart contract that calls 5 smart contracts in a row, so the return data will be the one that was returned from the latest call. So this like return data is always updated. And usually return data is ABI encoded as well, regardless of the opcode used. So if you're returning variables from the function, those variables will be ABI encoded. If you are reversing some errors or reversing the string that represents some error. This string or those errors will be ABI encoded as well. This is just a convention, so the front end may like parse those arguments and present them to real users in a more comfortable way or more convenient way. And where can you learn more about opcodes, data allocations, what those opcodes do, how they consume values, how they push, like what they push to the stack, and what like opcodes are available in Solidity or EVM, etc., etc. So this is one of my actually favorite websites, and to learn and recollect something about EVM, like I know precompiles, and etc., etc. Its name is EVM Codes. I really recommend like checking it out. It is super neat, super cool. Like sums up for the creators of this website. So yeah, just check it out. And that's it for today. So if you have any questions, please ask.
Okay, yes, time for question. So it was not simply a lecture, but I hope it was very interesting. Okay, thank you so much, and wait for new tasks and new meetings. And I repeat, Ilya will definitely do all tasks on all answer the near future. Okay.
Yeah. So you will receive a practical task, I believe, like in an hour. And just as always, it won't be hard, but it will be interesting, I believe.
So have a nice day, and nice to meet you. Okay. Bye-bye.
Yeah, bye.